Greetings everybody and welcome back to another video. It's been quite a while once again since my last complex analysis content integration video here on this channel. I've just been super busy. I've been all over the place. It's the holidays, but I'm still busy somehow. I don't even know. But today's a bit of a special video because we have a special guest coming on today. You may have heard of him actually. Well, his name's in the title of the video. He's Kamal from Maths 505, the absolute integration god. He's mastered the Feynman technique for integration, and he destroys every single one of my integrals, or almost every single one of my integrals here on this channel using the Feynman technique, which is pretty cool. So today we're taking a look at this integral, negative infinity to infinity of sine squared of x over x squared times x squared plus 1 in the denominator. And my boy Maths 505, he'll be going first. He'll be destroying this integral using some real techniques, and then I'll be coming on. And then we'll take a look at this using a complex method, so contour integration. So I hope you guys enjoyed this video. Let's welcome Maths 505 on to present the real method to this integral.
Ladies and gentlemen, this is your boy Kamal from Maths 505, and today we have this absolutely insane looking integral that we're going to solve using real versus complex techniques. And here's my solution using real analytic methods. Now my approach here will first be to resolve the denominator into its partial fraction decomposition. So we can write this as the integral from negative to positive infinity of the square of the sine of x times, now the partial fraction decomposition here is quite simple. It's 1 by x squared minus 1 by x squared plus 1. Quite easy to see this. And this means that we have two integrals. We have one from negative to positive infinity of the square of sine x by x squared minus the integral again from negative to positive infinity of the square of the sine of x divided by x squared plus 1. And this integral here, the first one on the right hand side of the equation, is in fact quite easy to evaluate. So if I use integration by parts here, I'll get something quite familiar to us. So I'm going to differentiate the trig function and integrate the 1 by x squared term. So that should give me negative 1 by x times the square of the sine of x, with the limits of integration being negative and positive infinity. Okay, cool. And minus the integral from negative to positive infinity of, I'll have another negative sign here, so that will cancel out this one outside. So I'll have 1 by x, and the derivative of the square of the sine of x is in fact twice the product of the sine and the cosine of x. Now this term here evaluates to 0 because the square of the sine of x is just a bounded function, whereas the limit of 1 by x as x goes to either positive or negative infinity is 0. So that leaves us with the integral from negative to positive infinity, and we can write twice the product of sine and cosine of x as being the sine of 2x, right, using the double angle formula. So this is a Dirichlet integral that we're quite familiar with, which evaluates to pi. So this implies that our integral I equals pi minus the integral from negative to positive infinity of the square of the sine of x divided by x squared plus 1 dx. And now because the integrand in this integral on the right hand side is an even function, instead of integrating from negative to positive infinity, we could just integrate from 0 to positive infinity and double the result. And this factor of 2 is in fact quite useful here, because if I introduce it upstairs over here, then I can expand this using trigonometry as being 1 minus the cosine of 2x. So I equals pi minus the integral from 0 to positive infinity of 1 minus the cosine of 2x divided by x squared plus 1 dx. And once again, we can write this as the integral from 0 to infinity of dx by x squared plus 1, quite familiar. Two negatives give you a positive, so we have the integral from 0 to infinity of the cosine of 2x divided by x squared plus 1. And this integral here, it evaluates to the inverse tangent of x, with the limits being 0 and infinity. And as x approaches infinity, the inverse tangent of x approaches pi by 2, right? And as x approaches 0, the inverse tangent approaches 0 anyway. So we can replace this integral with pi by 2. And pi minus 1/2 of pi is just 1/2 of pi, right? So here's the structure of our integral I now after much simplification. And this interesting looking integral here is what we're now going to evaluate using Feynman's trick. So let I of t equal the integral from 0 to infinity of the cosine of tx divided by x squared plus 1. And let's assume that t is a positive real number. Now that we have the integral function I of t, we can now take the derivative with respect to the parameter t. And now for the golden question, can we switch up the order of the differentiation and integration operators? Well, we see that there's no problem, there are no problems with respect to boundedness or convergence, right? So yes, indeed, we can perform the switch up, and because of the switch up, this total derivative will be converted into a partial derivative with respect to t. So we're differentiating partially with respect to t, the cosine of tx divided by x squared plus 1 dx. And oh, I forgot to point out here, well, it's pretty obvious that we're interested in the case for t being equal to 2. Okay, anyway. So now if we take the derivative with respect to t, and because we're differentiating partially with respect to t, we're holding x constant, right? So that means this 1 by x squared plus 1 term is a constant, and we're left with sine of tx, and because of the chain rule, we're going to have this factor of x being multiplied as well. And oh, the derivative of the cosine function is negative sine. So, okay, so this is a structure for the derivative of I with respect to t. It's the integral from 0 to infinity of negative x times the sine of tx dx by x squared plus 1. And now we're going to perform some trickery here. So what I'm going to do is I'm going to multiply downstairs and upstairs by a factor of x. So that gives me this modified structure. And for an extra element of trickery, I'm going to take this x squared term here and add a 0 to it, meaning I will add 1 and subtract 1 at the same time. So what benefit does that have? Well, if I isolate this x squared plus 1 as a single term and then apply the distributive property, I will have the integral from 0 to infinity, a negative sign here, of x squared plus 1 times the sine of tx divided by x times x squared plus 1 dx, and two negatives will cancel out, so we have a plus sign, integral from 0 to infinity of sine tx divided by x times x squared plus 1 dx. So the x squared plus 1 factors cancel out, and we're left with the negative of the integral from 0 to infinity of sine tx dx by x, which is once again the Dirichlet integral that has been following us around quite a bit in this video. And with these limits, it evaluates to pi by 2. Okay, cool. Plus this integral from 0 to infinity of sine tx divided by x times x squared plus 1 dx. And this is the entire structure for the derivative of I with respect to t. Now we're going to differentiate with respect to t again. So that gives us the second derivative of I with respect to t. And the derivative here is 0, of course, because pi by 2 is a constant. And for this integral, we're going to again apply the Leibniz rule. So we have the integral from 0 to infinity, differentiating partially with respect to t. That means you're gonna get the cosine of tx, and using the chain rule, you'll have a factor of x divided by x times x squared plus 1 dx. And the factors of x cancel out quite nicely here, and you're left with the integral from 0 to infinity of the cosine of tx divided by x squared plus 1, which is in fact our integral function I of t. So that means you have quite a nice differential equation here, where the second derivative equals the function itself. And the general solution to this is I of t equals some constant c sub 1 of e to the negative t plus another constant c sub 2 of e to the positive t. We now have to figure out the values of these two constants, c sub 1 and c sub 2. And for that, let's recall our integral function I of t. Okay, so this is what it looked like, right? You have the cosine of tx divided by x squared plus 1. And you can derive some information about our function I of t using this integral structure. And if you plug in t equal to 0, you get the integral from 0 to infinity of the cosine of 0 is just 1. So 1 by x squared plus 1. Again, quite familiar, our arctangent friend. And this equals pi by 2. So we know that I of 0 equals pi by 2. And you can eliminate one of these two constants quite elegantly using a simple analysis. Look here at the structure of this integral. The cosine of x is a bounded function, right? And the other function, 1 by x squared plus 1, which is being multiplied by the cosine of tx. Now, this here is a decreasing function on our interval of integration. So by a theorem, I think it was called Dirichlet's convergence theorem. So yeah, I'm pretty sure it's that. By that theorem, the integral converges to something, right? It has a solution. Okay, cool. So because the cosine of x is a bounded function for any real value of t, and we're taking t to be a positive real number in this case, because it's bounded for all positive values of t, that means our integral function, the integral should be convergent for all values of t, no matter how big or small they are. As long as the structure is in place, the integral will converge for any value of t. That's great. Why is that great? Because if I take bigger and bigger values of t, that is, I'm talking about taking the limit as t goes to infinity, in that limit, for our integral to be convergent, we need this term here, we need this term c sub 2 to be 0. We need it to be 0 so that we're rid of this exponential term with a positive argument. So this argument over here, this analysis implies that c sub 2 is 0. And that means I of t is just c sub 1 times e to the negative t. And using our initial condition here, that I of 0 equals pi by 2, it implies that pi by 2 equals c sub 1 times e to the 0, which is 1. So there you go. We have our other constant of integration. So this implies that I of t equals pi by 2 times e to the negative t, and we were interested in I of 2. So I of 2 equals pi by 2 times e to the negative 2, and which can be written more elegantly as pi by 2e squared. So plugging in this information into the structure we derived for our integral I, that was the integral from negative to positive infinity of the square of the sine of x divided by x squared times x squared plus 1 dx. And this equaled, let me recall, from up here, yeah, this was it, the one in green. So it's pi by 2 plus this integral that we know what it evaluates to now. So we have pi by 2 plus pi by 2e squared, which is quite a nice result. Anyway, I hope you enjoyed the evaluation of this integral using real techniques. Now it's over to my boy Q Cube 3 to solve it using some beautiful contour integration.
That was a pretty sexy solution, if you ask me, seeing Feynman technique and differential equations popping up. That was, very, very cool. But yeah, let's take a look at the complex solution now. So first what I want to do is let's call this integral something. Let's call it I so we can refer to it later. And first thing we want to do here is with the sine function. We don't really want to use sine in the complex plane because it doesn't really behave nicely in the upper half plane, especially when you go out to infinity. So what we want to do is replace the sine with some kinds of complex exponential. Now, if this is just a sine here, we could just replace it with the imaginary part of e to the iz or something like that. But notice we have a squared here, so we can't really apply that directly. Instead, what we have to do is we have to reduce that power somehow, and the best way to do this is just use the cosine double angle formula. So what we can do actually is use this following identity: cosine of 2 times x is equal to 1 minus 2 sine squared of x. Now we want to rearrange for sine squared, so if we do that, we're going to get sine squared of x, that's going to be equal to 1/2 of 1 minus the cosine of a 2 times x like so. And this is nice because now we have a cosine function and it's only raised to a power of 1. So we can replace this guy with, let's say, the real part of e to the, in this case, it's going to be 2 times I times x. So this is going to be, we can pull the real part operator out the outside. So this is real part of 1/2, 1 minus e to the 2 times I times x. Okay, and this is quite nice because now we can put this back into our integral, and we can even bring the real part operator out to the outside of the integral as well. So this is going to give us, let's put the 1/2 outside actually, so we have 1/2, the real part of the integral from negative infinity to infinity. That sine squared of x now turns into 1 minus e to the 2 times I times x, and now we still divide by x squared over x squared, and then plus 1 integrated with respect to x, and yeah, this is our integral now. Okay, so now we have this nice function that we could potentially integrate in the complex plane. So now let's introduce a new function, let's say f of z, and we'll just let that be equal to, we have 1 minus, instead of all these x's here, we're going to have z, so 2 times I times z, divided by, we have a z squared, and then a z squared plus 1, like so. Now notice with this function over here, we're going to have a few poles going on. In particular, we have a double pole at z is equal to 0. And also, notice we have a z squared plus 1 factor in the denominator. We can factor that into z minus I, z plus I. So that's going to give us poles at z is equal to plus or minus I, like so. So that's pretty much everything we need to know about our complex function. Now let's try to draw up some kinds of contour and yeah, see what our contour should look like. Now we know there's going to be poles at 0, and then we have one at I here, and then one at negative I. And what we want to do is we want to integrate from negative infinity to positive infinity. So let's go for some negative r value up to some positive r value, and then it will take r to infinity at the end as well. And then what we want to do is we want to recover the integral on this interval here. Now we can't really go past 0 because, well, there's a pole at 0. So what we have to do is stop some distance epsilon away, and then we have to make a detour over to the other side. So like a little indent, you could say. And then we want to turn this into a contour, of course. We need to close it. So the best way to do this is just to introduce some circular arc in the upper half plane like so. Let's call this contour here C. We'll call the path going around big gamma, the path on the inside little gamma. And yeah, we'll traverse in the positive orientation as always, which means going anti-clockwise. Okay, so this is the contour that we're going to work with to get our integral I back. Okay, so first thing to do, let's write out a few integrals here. So we have the contour integral over C. This is going to be equal to the integral from negative r to negative epsilon, plus the integral from epsilon to r, so along the real axis here pretty much. Then we also have the integral over this little gamma path that goes around 0. And then finally the integral along the big gamma path like so. Now, first of all, let's take a look at this contour integral over C here. What exactly is this contour integral going to evaluate to? Well, we can use Cauchy's residue theorem for this, because notice this whole entire contour, it's not completely analytic in the domain because we have a simple pole at I here, which means we need to use the residue theorem. So let's do that, let's do it over here. So the contour integral over C of f of z dz, that is going to be equal to, well, Cauchy's residue theorem, it's 2 pi I times, well, the sum of the residues, but we only have one residue in this case in particular at z equals I. So residue at z equals I of our function f of z. Okay, but this is equal to 2 pi I. What's the formula for a residue at a simple pole? Well, it's just the limit as z approaches the pole of z minus a pole, so z minus I, times the function f of z, which in this case is 1 minus e to the 2iz, divided by, we have the z squared here, and let's factor that z squared plus 1 into z minus I, and then a z plus I. And notice that this z minus I, that's going to cancel with this z minus I over here, and we're safe to plug in z equals I into the remaining parts of the function, because nothing's going to blow up or anything. So this is going to be equal to 2 pi I. We have a 1 minus. What happens if you plug an I into this z here? Well, we're going to get e to the 2 times negative 1, which is e to the negative 2. So we have 1 minus e to the negative 2 over there. Okay, and how about this z here? Well, if you plug the I into there, you're going to get a negative 1 down here. And how about this z plus I? Well, you're going to get an I plus I, which is exactly 2i. Okay, so this is basically the contour integral done. Let's simplify a few things. So first of all, this 2 and this 2 cancel. This I and this I will cancel. Well, what remains is exactly a pi over here. Now we have this negative one. We can bring that into the numerator to switch those two terms around. So that's going to be, yeah, pretty much 1 over e squared, and then we have a negative one like so. So this should be the value of the contour integral over c. It's this nice little result over here. Okay, so now that integral is done, the contour integral over c is done. Let's take a look at these two integrals next. So the integral that go from negative r to negative epsilon, then epsilon to r. What we want to do with these two integrals, by the way, is we want to take the limit, so this is one integral done, we want to take the limit as r approaches infinity and epsilon approaches 0 of those two integrals, so negative r to negative epsilon plus epsilon to r. Now, what's going to happen in the limit? We're basically going to be able to recover the integral from negative infinity to infinity. And if you want to be technical, this is actually the principal value integral. Now, what exactly are we integrating? We're going to be integrating, just the function f of z over here. But notice what exactly is this guy? Well, on the real axis, you can even replace this z with an x because we're on the real axis. We're just going to get this integral back over here. And this is nice because this is basically where we're going to get our original integral I from, because if we take the real part of this integral, like we need over here, then just divide that by 1/2, we're going to get back to our I. So that's what we're going to worry about at the end of the video once we got all the other integrals done. Okay, so contour integrals done. These two integrals, we've basically figured out what it becomes. Now let's take a look at the integral over little gamma. This one's going to be a little bit interesting here. So integral over little gamma of f of z dz. Now, because this integral, it's going around a pole, not a branch cut, the value of this integral is not going to vanish. So we don't really want to make some estimations over here and show it goes to 0. Let's evaluate this guy directly by introducing a bit of a parametrization. So how do you parameterize the path of gamma here? Well, it's a little semicircle of radius epsilon, so it's not too tricky to do. Let's just use the parametrization. Z is equal to epsilon e to the I theta, where theta runs, well, where are we running from and to? We're going from an angle of pi here back to an angle of 0, so theta is going to go from pi back to 0. And okay, let's take a look at dz, the differential. Just differentiating this guy using the chain rule. It's I epsilon e to the I theta d theta. So this is the parametrization we'll plug into the integral now. So now we have the integral running from pi up to 0 of the function f of z, but we're going to replace all the z's in our function f of z with precisely epsilon e to the I theta. So what do we have first of all? We have a 1 minus e to the 2 times I. Now z is going to become epsilon e to the I theta. We divide this guy by z squared, but that's epsilon e to the I theta and squared. And then we also have, epsilon e to the I theta squared plus 1. And then we also have a dz, but we know what that becomes. It just becomes I epsilon e to the I theta integrated with respect to theta, like so. Okay, so now we can cancel a few things, and a few things we can pull out of the integral as well. In particular, this epsilon e to the I theta here, the squared will cancel with one of these factors, so that's gone. We can bring the I outside the integral as well, and also we might as well reverse these bounds over here, so we'll bring an extra negative sign out. So we have negative I, integral from 0 to, pi, of 1 over, we have epsilon e to the I theta, and then also 1 over, let's see, epsilon e to the I theta. This guy is squared, and then plus 1. And then we're going to have 1 minus this e to the 2i stuff here. Now, what we're going to do with this exponential term here is we're actually going to use its Taylor series expansion, because we kind of want to get rid of this epsilon e to the I theta here, because you can imagine we want to take epsilon to 0. If we have an epsilon down here, then it's going to completely blow up because we're dividing by 0 essentially. That epsilon there is basically fine because we have 0 plus 1 in the limit, pretty much, in the denominator, so that's fine. We need to take care of this first factor. And the only way to really kill off this guy over here is to expand out this exponential junk at the top there using a Taylor series expansion. So we have 1 minus. How does the Taylor series go? Well, it's the sum over here from k is equal to 0 to infinity. And what you do is you take the exponent, which is 2 times I epsilon e to the I theta, you raise it to the kth power, and then you divide everything by k factorial like so. Okay, and then we can integrate with respect to theta. Now, let's notice one thing over here. What is the first term of this series? Well, what happens when k is equal to 0? You're going to get stuff raised to the 0, which is 1, divided by 0 factorial, which is also 1. So in fact, the first term of this guy is precisely equal to 1. Now, notice we also have a 1 out over here, and because the first term is a 1, we're basically going to cancel with this 1 over here, which is pretty cool. So we have a cancellation with this 1 here. Okay, but then as a result, we have to start the index at k is equal to 1 instead, because the k equals 0 term is going to disappear. Okay, now once this 1 over here is gone, well, we can bring the negative out to the front if we want to. So I guess negative over here will cancel with the negative out the front, which is nice. Notice one thing, we can actually bring this factor of 1 over epsilon e to the I theta. We can bring this guy over here into this sum because it's independent of k. It's basically just a constant. And if you do so, what's going to happen is that this epsilon e to the I theta, well, there's one factor down here. It's going to cancel with another factor of epsilon e to the I theta here. Now let's be careful because we don't want to touch this 2i here. So let's put the 2i inside of its own little bracket, raised to the kth power. Okay, and then we have the epsilon e to the I theta. And what we're going to do is simply reduce the power by 1. So it's going to be k minus 1 there. And this is fine to do because we're starting the index at k is equal to 1. So we're not going to get negative powers or anything silly if we just put a negative 1 there. Okay, so this is really quite nice. This simplifies our integral quite a bit actually. So now we're left with I times the integral from 0 to pi. This guy is gone, so we only have that 1 over, all that junk that's still left. So epsilon e to the I theta squared and then plus 1. Now we still have this ginormous sum here to deal with. Now what I want to do with this sum is just write out the first term of this sum. So what happens when k is equal to 1? Well, we're going to get a 2 times I, okay, and then k factorial, 1 factorial, it's just a 1, so I guess a 1 down here. And then we have epsilon e to the I theta raised to the k is equal to 1. Minus 1, so that's just a 0 pretty much. So here that all cancels and that's a 1 pretty much as well. So the first term is basically just a 2i. And then we still have the rest of the sum. So we've written down the k equals 1 term, so now our sum starts at k is equal to 2, runs up to infinity of all the stuff that remains. And I guess the most important part is the epsilon raised to the k minus 1 factor. That still remains there. Everything else in this bracket, well, they're just constants pretty much. So all that is done, so now we have a d theta still. Okay, so now we're basically ready to take the limits as epsilon approaches 0. And I'm just going to assume we can pull the limits as epsilon approaches 0 inside of the integral and inside of the sum as well. If you want to do this more rigorously, you can use dominated convergence theorem. But let's just assume we can bring the limit inside. So in the limit as epsilon approaches 0, what exactly is going to happen to this integral? Well, we're going to have the I that's still there. Okay, now as epsilon approaches 0 here, we're going to get essentially 0 plus 1, which is just 1. So this factor, well, it just turns into 1 pretty much. Now we still have integral from 0 to pi. We have 2i as the first term here, so 2i, okay. Now how about the sum over here? Each of the terms of the sum has some sort of epsilon to the k minus 1 factor. And because k is starting at 2, we're always going to get an epsilon to a power of at least 1. So because we have those epsilon factors in the limit as epsilon approaches 0, all the terms in the sum here are basically going to vanish, which is pretty cool. So we essentially are left with a plus 0, so we don't even have to write anything there. So we're just going to finish off with a d theta. So we've simplified things quite nicely. This is in the limits as epsilon approaches 0. And now, well, we have an I and an I, so that's just negative 1. So we have negative integral from 0 to pi of d theta is exactly just a pi. And then we also have this 2 here. So that's going to be a negative and then a 2 pi, like so. Okay, so we've gotten the integral over this gamma here figure, this little gamma. We got a negative 2 pi, which is quite nice. Now the last thing to, I guess, discuss, we're not really going to do it just to keep this video shorter, is the integral over this big gamma here. It turns out this integral, it's going to go to 0 in the limit as r approaches infinity. Now why is that the case there? Well, you can take a look at Jordan's lemma if you want. I've made a video of the proof of Jordan's lemma, which you can check out. It's probably in the description somewhere. But if you take a look at a function here, you can kind of break up the function across this negative sign and just apply Jordan's lemma twice, because on the first term, you're going to get 1 over some kinds of polynomial, so applying Jordan's lemma, that of course goes to 0. And then on the second term, we have e to the some real number times I times z divided by polynomial. And that's the exact form that Jordan's lemma takes pretty much. So on that second term there, you can also apply Jordan's lemma and it also goes to 0. So overall, the integral over gamma goes to 0. And yeah, let's just leave that as an exercise to prove if you want to show it rigorously. Okay, so we're basically done with all the integrals now. Now it's just time to put everything together to wrap up the video. So first of all, we have the contour integral over c there. What exactly is its value? It's going to be pi. Let's write it out this way. We'll expand out the sky. So we have a pi divided by e squared, and then we have a negative pi. So this is the left-hand side. And then we have these two integrals next. What exactly is that going to evaluate to? Well, it's going to be integral. So this is equal to integral from negative infinity to infinity of the function f of z dz. And then we have a plus the integral over gamma there. Now, what is the integral over gamma? Well, that's going to evaluate to negative 2 pi. So we have a negative 2 pi here. And then finally, plus the integral over big gamma, which goes to 0. Okay, so now we have this equation we need to solve. It's not too tricky to do because this 2 pi, you can add it to both sides. So yeah, this is basically gone over here. And then we're going to turn this negative into a positive because negative pi plus 2 pi is positive pi. Okay, so we have the integral from negative infinity to infinity of our function f of z, and this is what we're going to use to recover our original integral I there, because the first thing we need to do is just take the real part, but notice that guy over there, that's already a real number, so we don't have to worry about that, and then we just need to times it by a half to get back to our original integral I, which is pretty cool. So basically, I is just going to be 1/2 of pi over e squared plus pi, and so I guess we could simplify this a bit more if we want to. That's going to be exactly pi divided by 2e squared, and then plus an extra pi over 2, and this is going to be the final result, which hopefully, yeah, this is the exact same result that Maths 505 got using the real method as well. So that's basically all for this integral here. That's all for this video. Hopefully you guys enjoyed both methods. It's probably a fairly long video already, so if you've made it the whole way through, then thank you very much for watching. Make sure to subscribe to Maths 505, so his link will be down in the description. And of course, yeah, you can subscribe to me as well if you like the complex analysis and want to see more and whatnot. But yeah, that's going to do it for today. Once again, hope you guys enjoyed, and until the next one, have yourselves a wonderful day, and I'll see everyone in the next one. Bye-bye.